Hello, my name is Marcell Vazquez-Chanlatte, a PhD candidate at the University of California, Berkeley. Together with my advisor, Sanjit Seshia, I have been working on the theory and tools for communicating formal specifications through demonstrations. In this talk, I will discuss our recent work on inferring specifications from demonstrations using the principle of maximum causal entropy. To begin, I'd like to start with some high-level motivation. At the highest level, this research aims to enable human-robot interaction. To that end, physical demonstrations are a natural way to express tasks and relay intent. However, in the context of formal methods, it's often unclear how to best leverage this information. In particular, within the context of formal methods, one often presumes the existence of a system and a formal specification. For example, verify the system on the right satisfies the specification on the left. However, in practice, this is rarely the case. This is because, even for experts, writing down a formal specification can be non-trivial and time-intensive. This is why we've been interested in developing techniques for inferring formal specifications from demonstrations. However, working with demonstrations comes with its own set of challenges. To start, demonstrations are often noisy and contain errors, either due to user mistakes or stochastic transitions. Furthermore, demonstrations are often unlabeled, since they come from logs, or, in the case of real-time collaboration, may not yet be over. Next, demonstrations are often given within some context. For example, one might provide a natural language description of the task. Here, avoid red while reaching yellow. Or there may be a task-specific prior based off the domain. Finally, and perhaps most importantly, demonstrations are often ambiguous and do not uniquely define a specification. However, our aim is to provide a partial ordering between specifications so that one can say which of the two specifications is more likely. For example, did the user intend to avoid lava? Is it more likely that they were trying to avoid lava or not? To recap, demonstrations are noisy, unlabeled, contextual, and ambiguous. Thus, our goals for this work are to have a noise-resistant, unsupervised, and Bayesian method for inferring formal specifications from demonstrations. To this effect, our contributions are as follows. Formulate a robust inference method using the principle of maximum causal entropy. Compared to our prior work, this method supports stochastic environments. Next, we provide an efficient implementation based on binary decision diagrams. Finally, we provide an experimental validation of this method. The structure of this talk mirrors the contributions. In particular, we'll start with the problem setup, provide a naive problem formulation using the principle of maximum causal entropy, provide a more efficient encoding using binary decision diagrams, and wrap up with an experimental validation. To begin, let's set up some basic definitions. We're going to assume that there's a fixed set of states and actions. For example, in this grid world, states are positions, and actions are attempts to move up, down, left, and right. More generally, we're going to assume that we're operating in a Markov decision process. A trace is a sequence of states and actions. For simplicity, we're going to assume that all traces are the same length, tau. A Boolean specification, then, or a trace property, is a set of traces. In practice, one doesn't typically describe the set of traces in a specification, but rather one provides an abstract description in a formalism such as logic, automata, or epsilon optimality. Furthermore, it's important to note that Boolean specifications don't provide an a priori ordering between traces, and it is in this way that demonstrations differ from normal labeled examples. In particular, a demonstration of a task phi is an unlabeled example where the agent tries to satisfy the specification. For example, in this image, we see an agent attempting to reach the yellow tiles while avoiding red tiles. However, due to wind, the agent slips downward and enters the red tile. What's important is that even though this is a negative demonstration, the actions and the implicit dynamics probabilities provide enough information to realize that the agent did not intend to enter the red tile and was most likely trying to reach the yellow tiles. Here, agency is key. So is a notion of an action. And in particular, the dynamics plus the actions induce an ordering based off of the success probabilities. Once we know the dynamics, we can say that this left trajectory and control policy is better than the right policy. We're now ready for an informal problem statement. In particular, we're going to assume that there's a demonstrator and a learner. And because of the way that demonstrations work, we can ask, is it likely that the agent would generate a given set of demonstrations given a particular abstract task. In particular, we're going to assume that the demonstrator or agent is operating in a Markov decision process while trying to satisfy some unknown specification. And then, given a sequence of demonstrations and a collection of specifications, we're going to ask to find the specification that best explains the agent's behavior. In order to do this, we're going to need two ingredients. First is we're going to need to know how to compare specifications, and that's going to be the primary focus of this work. The second ingredient is a way to search for likely specifications, and we're going to leave that as future work. We are now ready for a naive problem formulation. In particular, we're going to do so by reduction to inverse reinforcement learning. As a reminder, in inverse reinforcement learning, one assumes that an agent is acting in a Markov decision process and is optimizing the sum of unknown state rewards. In inverse reinforcement learning, one is given a series of demonstrations and asks what reward R best explains the agent's behavior. The problem is, there's no unique solution posed to this problem. A common idea, and a very successful idea, in inverse reinforcement learning has been to disambiguate using the principle of maximum causal entropy first introduced by Zbart in 2010. Now, while I don't have time to formally go into all the details of the principle of maximum causal entropy, I do have time to provide some intuition and basic definitions. The causal part of the principle of maximum causal entropy simply means that we want to causally condition random variables on each other. In our context, this just means that the current action shouldn't depend on information from the future. For example, imagine developing a forecasting policy. Causally condition just means we shouldn't be able to condition on the fact that the agent is at the marked location at time t+2. The key idea of the entropy part of the maximum causal entropy is to not overcommit to any particular prediction more than the data forces you to. In particular, we'd like to minimize the surprise of actions subject to feature matching constraints. This idea is formalized by the notion of causal entropy. Here, whenever I say feature matching, I'm going to mean matching the satisfaction probabilities. So the forecasters that we use are going to be just as competent at the task as what we see in the data. To get some intuition about what optimizing this quantity would mean, let's consider the minimum entropy forecaster, which would put all of its probability mass on a single path. Then, if the demonstrator provides another demonstration, which is equally good according to the specification, but it is not this path, the agent would be very surprised. Conversely, the maximum causal entropy forecaster would hedge its bets and exponentially prefers high-value paths, but doesn't assign zero value to low-value paths. The key takeaway is that maximum causal entropy results in a robust forecaster. And this gives us an explicit way to answer this comparison of what's more likely, the left specification or the right specification. For our reduction, it suffices to consider linear rewards, where the reward is a linear combination of state features. Now suppose we observe or feature match to the expected value of the features. The principle of maximum causal entropy prescribes the following policy, where the Q and V values are defined via soft Bellman backup. The state value, V, is simply the log sum of exponentials of the action values, and the action value is simply the expected state value after applying the action plus the current state reward. This soft Bellman backup defines a family of policies indexed by theta. If one simply fits theta to match the data, Zbart proved that this policy is the one with maximum causal entropy. Finally, in order to complete our reduction, we need to decide what the reward should be. As we stated earlier, we'd like that a priori we shouldn't be able to distinguish between two traces that both satisfy the specification. A natural proposal then is to use the set indicator for the specification. We need to be careful though, because states are now traces. Consider the example on the screen. Let's add some explicit transition dynamics to make this a Markov decision process. Great. Now, consider a specification over lengths of trace 2. Lifting this MDP would result in the following tree. What's important is that states now correspond to paths in this unrolled tree. With this tree in mind, let's focus on the soft Bellman backup. For notational convenience, let's replace the log sum of exponentials with smooth max, denoted here by the symbol S-max. Now, in the context of our tree, the soft Bellman backup corresponds to the following computation graph, where we've replaced f with the indicator function for whether or not the specification is satisfied. Here, we have a graph that takes as inputs either 0 or theta if the specification is satisfied, and alternates between expectation and softmax. Furthermore, it can be shown that the satisfaction probability grows monotonically in theta. Thus, in order to compute a maximum causal entropy forecaster that matches the demonstrator's competency, one can simply binary search for the appropriate theta. At this point, we could evaluate the likelihood of any given specification. However, in practice, this probably wouldn't be a good idea since these trees grow exponentially in the horizons, and thus even for toy problems, this would become quickly infeasible. We're going to leverage the following two observations to make this problem tractable. First, note that this tree has a lot of shared structure, and that most of the computation graph is redundant. This is due to the binary nature of rewards and the limited number of operators used in this expression. Second, I'd like to point out that the system and environment actions are ordered. Together, these suggest a natural encoding as a binary decision diagram of this tree, and will show that we're going to be able to adapt our soft Bellman backup to this binary decision diagram. We provide a summary of our procedure in the following figure. To begin, we take in a fixed dynamical system and a candidate specification. Together, these produce a binary decision diagram which induce a particular encoding on the demonstration as bit vector. In parallel, we take this binary decision diagram and we form a modified soft Bellman backup to compute the maximum causal entropy policy over this binary decision diagram. Together with the encoded bit vectors, these produce likelihood estimates that we're able to use to compare specifications. However, in the interest of time, we're going to focus on just describing the binary decision diagram encoding with the other details provided in the paper. Our binary decision diagram encoding centers around the following idea of modeling a Markov decision process as a deterministic transition system with access to NC coin flips at every single round. So for example, you can have a dynamical system that takes in state, an action, and some coin flips and produces the next state. Next, for simplicity, we're going to assume that the number of actions is the power of 2. This assumption is relaxed in the paper, and we'll leave details there. Now, together with these two assumptions, we can write our dynamics as a function from state and a bit vector to a next state. Thus, using self-composition and composition with a specification, one can rewrite the entire unrolled tree as a binary predicate. As we proposed earlier, we're going to represent this predicate as a reduced ordered binary decision diagrams in the particular order that we're going to use, what we're going to refer to as the causal order, where the action bits precede the coin flip bits at every single time step. Given a fixed causal ordering of the bits, any predicate psi can then be represented as a unique, reduced ordered binary decision diagram, completing our encoding. A natural follow-up question then is, can you efficiently compute the maximum causal entropy policy on these binary decision diagrams? The answer ends up being yes due to 3 facts. The first is that softmax and expectation are associative. The second fact is that when softmax is applied with 2 identical arguments, this results in simply the argument plus a log2 factor. Similarly, when expectation is applied with 2 identical arguments, this acts as the identity function. This means that if we reinterpret our binary decision diagram as a computation graph, the associativity means that we can split the softmax operation across multiple bits, or the expectation operation over multiple bits, and if we have edges that are skipped over, we simply add a log2 factor for every softmax that's skipped over. Thus, the computation time is linear in the size of the binary decision diagram. A natural follow-up question then is, how big can these causal BDDs be? In the paper, we prove the following upper bound on the size of these causal BDDs. What's important about this bound is that it's linear in the horizon. Namely, the BDD can grow at most tau times the number of bits it takes to represent the actions and the environment actions, which are represented as coin flips, times the size of the composed monitoring automata, times 2 to the number of coin flips. Note then that using function compositions, one can build this BDD in polynomial time by incrementally unrolling the system. These size bounds have important implications on our overall inference procedure. Namely, after the BDD is produced, the encode, fit, and estimation steps are all nearly linear in the size of the BDD. This results in an efficient inference procedure for specification inference from demonstration. Finally, we validate our method with an experiment. For our experiment, we consider an agent operating in a grid world such as this. The agent can attempt to move up, down, left, or right. However, with probability 1/32, the agent will slip and move to the left. We provided 6 unlabeled demonstrations for the following task. Go to and stay at the yellow tile. We call out recharging. Avoid red tiles, so avoid lava. And if you enter a blue tile, which we'll call water, touch a brown tile before recharging. So this last one is informally known as don't recharge while wet. And do all of this within 10 time steps. And importantly, while 5 of the demonstrations are positive, the 6th demonstration, the one annotated as a dashed red line, fails because after it enters the water, it's unable to reach a brown tile due to slipping. We then ran our proposed inference procedure on a small concept class related to the demonstrated specification. We ran our inference procedure on the formula true, avoid lava, recharge, don't recharge while wet, and other conjunctive combinations of these formula. The demonstrated formula is the formula phi1 and phi2 and phi3. For each formula in our concept class, we computed several statistics such as the policy size, ROBDD build time, and the relative log likelihood compared to the trivially true formula. It's worth noting that the intended formula, phi star, has the highest relative log likelihood despite the fact that there is an unlabeled demonstration error. By contrast, formulas such as avoid lava, which have no counterexamples in the provided data, have very low relative log likelihood compared to true. This implies that our method is able to be robust to demonstration errors despite the fact that there are formulas that are exactly consistent with the data. If you're interested in exploring this data yourself or playing with our method, we've provided a hosted IPython notebook at the following URL. Furthermore, the code for this experiment can be found at the following GitHub repository. In conclusion, by leveraging the principle of maximum causal entropy, we've proposed a method for assigning likelihood estimations to demonstrations given formal specifications. This enables inference procedures that are noise resistant, unsupervised, and Bayesian. Furthermore, we provided an efficient implementation based off a reduction to binary decision diagrams. Finally, we've provided initial experimental validation of our method. Next, while in this work we've mostly focused on assigning likelihood estimates in order to be able to compare formal specifications, future work includes systematically searching for the most likely specification in a large concept class.